Hello, it's Doug. I'm back again with another one of these tutorials. And I just want to start with my normal disclaimer, which is that I'm not an electrical engineer and more of sort of advanced level hobbyist. And the reason I'm doing these videos is just because I learn about these things and then I get really excited. And I want to basically, my friend Sean was like, "Why are you making these videos?" I was like, "I'm making them for past Doug, proto Doug, because these are the videos that I would have liked to watch when I was learning about these circuits, and so I'm making these for, you know, people like me, basically." So this is going to be a video about the it's going to be about high voltage series regulation, voltage regulation, but it's going to be specifically about and leading up to the Madia regulator. And this is a well-known and often used regulator, and there are lots of different variations you can find online. I've created a couple of my own variations and done a PCB and done a lot of playing around with this on the breadboard, so it's a lot of fun. But we're not going to start there. We're going to start just at regular old voltage regulation and then work our way up, and then I'll be explaining how all these different circuits kind of work. So I think this stuff's really interesting and a lot of fun, and I hope you think so too. So the first circuit we're going to be looking at here is just what is inside LM317. So you might be familiar with LM317. It's sort of the most common 3-pin voltage regulator, and it's good up to about 40 volts and a couple of amps, I think 1.5 amps maybe, something like that. And it's more complicated than this if you actually look at the circuit diagram, but this is a sort of a simplified, this is all you really need to know about what's going on the inside to make good decisions and have a good understanding of sort of what to do with it. And so your positive voltage comes in here. It's going to drop some amount of voltage, and it's going to come out over here, and hopefully on the way out it's going to be regulated. And what regulated means is that if you have, you know, ripple coming in on the output, you will not. And so the amount of ripple that a device like this can remove is called the ripple rejection ratio or something like that. It's usually measured in dB. And about the best you can do with an LM317 is actually really, really good. You can drop about 80 dB if you know, if your layout is correct and your circuit is right and all of that kind of stuff. And so it's super, super effective, and I'm going to show you why it's so effective. So don't worry about this. This looks kind of complicated. It's a Darlington pair, and you can think about it as a single device. And so just think about it as a single series pass device where the voltage here is going to be determined by the voltage here, right there. And so basically, I mean, minus these two diode drops of 0.6 or whatever, they're going to drop right here. What you put here, you will get here, provided that you have sufficient voltage over here. And so that's how this device works. So it's basically your power device. This is sort of like the big power valve that's turning everything on and off. And all of the circuits we're looking at are going to include sort of like the power voltage pass device. Like some of them will be a FET, some of them will be this Darlington. You could use a single transistor here too, but a Darlington is better because it consumes very little current, because the current gain is amplified by the gain of the transistor. The current gain of the transistors are multiplied. Anyway, getting a little off topic here, but you can see that the base of this series pass device is run by this op amp. And op amps have really, really high gain, so much so that if these two voltages are ever slightly different, the output will basically just slam into the positive or negative rail. And so it has such a high gain. And so you can see this is being run basically without any sort of like feedback around it. It's because you want the gain. And so how this works is that 1/2 of the op amp here is connected just directly to the output here, and the other half is connected through this zener. And so this is a special kind of zener. It's a precision voltage reference they build into the chip, and they've made it even more effective by putting a current source here. And a current source just makes zeners more effective because zeners really only drop a specific voltage at a specific current. And if you raise or lower the current, the voltage will drift a bit. But if you put a current source here, then there's always the same amount of current going through the zener, and you're always dropping the same amount of voltage. So all you need to really know about this is that you're adding 1.25 volts to this pin. So whatever you put in here, you're going to add 1.25 volts to it. And so the next circuit we're going to look at is going to show us how to use the adjust pin to set a constant voltage out here using this series pass device and this op amp. So let me switch to that. Okay, so here, this is the basic regulator circuit that you're going to see. If you go to the LM317 datasheet, it's going to show you this is basically how you are supposed to run it. You use this voltage divider, and you know that this is going to try and adjust this right here for these two to be the same voltage. And so we know this one has got 1.25 volts added to it. And so we know it's going to try and make this one 1.25 volts different from this one. So you've got to subtract it off again, basically. But anyway, the way this works is the adjust pin is always looking to be 1.25 volts less positive than the positive V out here. And that's super useful because that fixed voltage that it's looking for allows us to set a constant voltage regardless of load and then regardless of the input voltage. And so let me briefly explain how this works. Don't worry about this math here. It'll make sense in a moment. You've got a voltage divider. This voltage divider drops all the voltage between V out and ground. And so if you know about voltage dividers, you know that the voltage is cut up evenly amongst the resistance. I guess that's the way to say it. I don't know if there's probably a better way to say it, but basically, let's say these were the same value. Okay, so you know you're getting 1.25 here. If they were the same value, you'd have 1.25 here as well. And you'd know that your output voltage up here would be 2.5 up here, right? Right. And so, but it doesn't have to be that way. There are any number of values here. You could make this some number of times the size of this resistance right here, and you can see how quickly the voltage would start to add up. And you can make this one smaller or this one larger all day long, and you'll end up with output voltages that are well in excess of the 40 odd volts that this chip can deal with. And so now that's a cross. So you could potentially put this in a circuit that's 300 or 400 or 500 volts for a tube amplifier, which is what I like to do with these things. As long as you were only ever dropping 40 volts across. But that's really tricky because let's say your wall voltage goes up or down or something like that, or you just, on startup or turn off, one of these caps tries to discharge less or more quickly than another cap on either side of this thing in the power supply, you're always going to exceed that 40 volts and destroy your chip. And really, you shouldn't be running it right at 40 volts. Anyway, but there's nothing stopping you from making a voltage divider here that would multiply this 1.25 volts by, hundreds and hundreds of times to end up with something like 400 volts out over here. You can totally do that. Now, it will never be able to accomplish that if it doesn't have more than 400 volts coming in here, and you would never do that because you would destroy your LM317. So that's how that works. The reason that it's regulated over here, so let's imagine for a second what's actually happening here. So let's say the output voltage goes up. So that would mean that this voltage right here would also go, so this voltage goes up, this voltage goes up. The voltage divider, as you can see, if the voltage up here goes up, this is gonna raise that 1.25 volts here. And so if it raises that 1.25 volts, it's going to come back over here and use the full gain of the op amp to sort of push it the other way. So I don't know how better to explain that exactly, but yeah, so it's negative feedback. It's negative feedback is how this works. You could also think of it like this. If this goes up, it's going into the inverting side of the op amp. So if this goes up, then this is going to go down. And if this goes down in voltage, then this will go down in voltage. So if it goes up in voltage, it goes down in voltage until it reaches equilibrium. If it goes down in voltage, then it goes up in voltage until it reaches equilibrium. And it's always looking for that 1.25 volts across this resistor right here. So that is how an LM317 works. And you see, like I said, you can't use this very effectively in a high voltage circuit, although you'd like to, because these things cost about $1. They're pretty tough. They don't die easily, and they're quite reliable. And like I said, they have a ripple rejection of some 80 dB if you use them correctly, which is far in excess of any sort of regular LC, L or whatever, RC that you typically see in a tube amp. And so if we could do something like this, it would be pretty great. But you don't have to do like this. So we're going to be looking at, so the Madia uses one of these in a high voltage application in a clever way, and we're going to get to that. But I should also point out before we get there that there are ways of doing this in a discrete way instead of using a IC. And we're going to look at those just so we know what the other options are before we jump straight to the clever Madia circuit. Anyway, let's go to the next one. All right, so here's a regulator made out of discrete components, and that's really good for high voltage applications because you can spec each one of these components yourself and make sure that they all will handle the voltage basically. And so you can build yourself a nice little high voltage regulator this way. And so the Madia regulator uses an LM317, and so when we get to that, that's the fun part in my opinion. But these are also very fun, and I've built some of these, and they are really effective. So how does it work? So you can see here, once again, we've got our series pass device. We know that whatever voltage is here is going to basically be up here. Not exactly perfectly because of these diode drops and all of that, but more or less. So you can think of this as a follower. This is a emitter follower here. And it's just a Darlington pair. It acts like a single transistor with a very high current gain. I think I already said that. Anyway, we got another transistor down here, and you can see that we're running the base here off of a voltage divider. So this looks already familiar to our LM317 situation. And so basically you can think of this just like the LM317, but instead of an op amp with, 100,000, gain of 100,000 or something like that, we've got a transistor here, and it probably has a gain of a couple hundred or something like that, but that's still very, very sufficient to make a very good and quiet regulator. But how is it regulating? Well, you see down here we've got a Zener again. And so basically the way this works is that the voltage here is going to be the same as the voltage here, except for this diode drop. So it's going to be that plus the 0.6 or whatever. So basically you take the value of this Zener and you add that diode drop from the base to the emitter, and then you know that you're going to get that voltage across this resistor. And so if you know the voltage drop across this resistor, you know what the voltage drop across this guy is going to be as well, because it's the voltage divider. So there's only one voltage that you can put in here that's going to result in the voltage that you need to have here. And so the way this works is that if this voltage goes too high, then this voltage goes too high. And if this voltage goes too high, then this junction is forward biased and this transistor turns on. If that transistor turns on, it pulls current through the load resistor here. And if it pulls current through the load resistor, voltage drops across this load resistor. If the voltage drops here, it brings the voltage down here and brings it down. So if the voltage goes down here, it goes down here. So, but if the voltage goes up over here, so if the voltage goes up over here, then it comes over here and it brings us down. So if the voltage goes up, it goes down. It's negative feedback. Now if the voltage goes down over here, this voltage will drop below this Zener plus the 0.6 diode drop. It turns this guy off, so there's no current coming through now. So if there's no current coming through here, then there's no voltage drop. So the voltage shoots up. So if the voltage shoots up, it goes up here, and that means it goes up here. So if it goes down, it goes up. If it goes up, it goes down. That's negative feedback for you. So that is how the circuit works. You need these. The reason you need these is that Zeners operate best at a specific current. And in the LM317, they've got a current source here. You could definitely put a little current source here if you wanted to, or a resistor, a properly spec'd resistor here. Will run the right amount of current that Zener, so it will stay at a constant voltage. R3 is the load for the the collector here of this transistor. It's what the voltage at the collector swings against. If you just plugged it straight in there, it wouldn't work. You have to have a load resistor. And those values, you have to sort of figure those out, do the math. That's sort of beyond the scope of the video. But the point of this is that you can create a high voltage regulator from discrete components. You can spec all of these transistors to be high voltage, and you can make these divider values whatever you like, and you can come out of this with a very nice high voltage regulator. So, let's see. Oh, another thing I wanted to show you is you don't have to use this for the pass device. So I have another info here. I have a graphic here I'll show you. So I just wanted to show you that instead of that Darlington, you can totally just use a MOSFET there. And works exactly the same way. Voltage here ends up being basically the voltage here with a little bit of a drop, but not much. Everything else works the same. This is just a protection Zener that just keeps the base from getting away from the source, or I guess the gate from getting away from the source. So on MOSFETs, instead of being the emitter, the collector, and the base, you have the source, the drain, and the gate. But otherwise, it's the same. So this also works just fine. All right, so here's another discrete regulator. I just wanted to show that you don't have to have negative feedback. You don't have to do error amplification with an op amp or a transistor. You can actually be much sort of more simple than that. And you can just basically take a pass device and regulate the voltage on the base with, I guess what we call is the shunt regulator over here. I guess that's what you would call it. But basically you just take some Zeners. You take Zeners and add them up to whatever voltage you want the base to be at, and then take a current source or a resistor and run, 5 odd milliamps through them to set the base. And out here, you're going to get whatever these added up to minus a small drop for your pass device out on the other end here. So that's easy. I've used these for like screen supplies and stuff like that, where it's not super critical that, that they have air amplification or they have super, they just work. This little circuit just works, and I use it sometimes for like a simple screen supply. Zeners can be kind of noisy, and so it's good sometimes to just take those and just take a little cap and just shunt some of that noise down to ground. You can see I've included the filter caps on this in and out, and I've also put a reverse polarity protection diode across this one. So this is a little bit more of a fleshed out circuit. Like this circuit would actually work. It's an N-channel enhancement mode device there, MOSFET. But this is, this actually will drop in. You could use this circuit just how it is. This is actually a current limiting circuit here, and we'll talk a little bit more about that because Madia, he includes this in his final version as well. And so, but we're just about to get to that, so let's move on. Okay, so here's the trick. Here's the trick that Michael Madia sort of figured out. Or I don't know, I mean, probably other people knew about this too, but he's the one that, he wrote up a white paper for Texas Instruments, and I'll link that in the description so you can have a look at it. Everybody should read through it. Back in 1980, and he basically just drew up a couple of circuits for how you could use like an LM317 in a 400 odd volt power supply, where it would regulate and do its nice little negative 80 dB ripple rejection thing and allow you to set the output voltage, but not blow up your regulator. So that's what he codified, I guess. And so let's look at how he did that. Okay, so here we go. This is the simplified version. You wouldn't want to implement it like this. It would work, but it needs some protection, a little bit more protection, to keep some things from blowing up when you turn your amp off or on quickly or something like that. But this is going to get the basic concept across. So you can see we've got 400 something volts coming in here. We'd like to get 250 out of here, and some power. You can actually run rather a lot of power through here, and it's mostly determined by how well you heat sink this device. But how does this work? So the idea that he had was to use a series pass device. Here we're using Darlington pair again, to drop almost all of the voltage and therefore dissipate almost all of the power between the input and the output voltage. And so the clever way that he did this was to put a zener, like a 10 volt or a 6 volt or something, I can't remember exactly what value he used, here, and a resistor here to run the zener. So we've seen all this before in the previous regulators using zeners. And so basically the voltage here is always going to be 10 volts added to the output voltage. And so that's extremely desirable, because what that means is that, because remember this is an emitter follower, so down here on the emitter, this voltage is basically going to be the same minus these two diode drops again. And so we're talking about the LM317 sitting in a 400 volt circuit, excuse me, in a 400 volt circuit where it only ever sees 10 volts across it. And so even though these values will be such to regulate to 250 or 300 or whatever volts you want out over here, of these pins on the circuit, on the chip, they will never see more than that 10 volts. So there's always going to be 1.25 here. And there's always ever going to be, less than 10, because you get these drops here. So let's say 8 or 9 right here. 8 or 9 volts. 8 to 9 here. Between here and here. And so this is pretty clever. Not only that, but I mean, if let's say you're dropping 150 volts here, so this drops 10, so this drops the other 140 right here. And so you got to size that so that it's correct to allow the 5 milliamps through here for that zener. And then of course you're going to have 140 right here across this device, and whatever milliamps you're wanting out, let's say 100 milliamps or something like that. So you can see this is going to get hot. It's dropping 140 volts or whatever at 100 milliamps. But the LM317, it's only dropping 8 or 9 volts at 100 milliamps. So it hardly even gets hot. It barely needs a heat sink. And so not only is it completely safe and doing its little 80 dB ripple rejection magic trick, it dissipates almost no heat, and it never sees more than 8 or 9 volts. So this is why everybody was excited about this, and lots of people have implemented this circuit in lots of different ways now, and there's lots of amplifiers and preamps and things that use it, because basically you get all the benefit of this $1 magic trick right here, with a couple of fairly inexpensive transistors, or you can use a MOSFET here, as we'll see in a minute, a zener, and a few resistors, and yeah. So I've built a bunch of these on the breadboard, and I've designed a PCB, and I'm designing another one now, and it's really cool. But this is not a version of the circuit you would want to use, because there are some things that need to be done here to make it more safe, like I said, for when you turn your amp on and turn your amp off and things like that. So let's look at the next version. Okay, so quickly, here we've got smoothing cap on the input and the output. That'll be like 10 UF over here, because you don't want to run a ton of capacitance after a regulator. And, you know, whatever you want over here, a 40 or 50 or 100 or whatever on the input. And the only other new thing about this drawing, obviously, we got a MOSFET here, just like on the previous regulator. You can drop that in for the pass device, and that works fine. So this is a source follower, just like the other one's an emitter follower. So whatever you get here, you get here. And this is always 10 odd volts above the output. So that works well. We've also got this right here. This is, once again, excuse me, this is our, let's see here. This is our protection to keep the source and the gate from getting away from each other. But also now, you'll see that this is actually a current limiter. And so if this drops sufficient voltage, which means it has sufficient current running through it, it'll actually turn off, it'll drop so much voltage that it will turn off this chip, which is a nice way to keep the circuit from destroying itself if you ever short the output accidentally, or if your output tube shorts or something like that. Anyway, let's look at the more final version then. We'll see what sort of a finalized version of the Madia regulator looks like. All right, so there's a lot of stuff added onto this, and that's why we started simple, because I find a lot of times people will post a schematic and it looks like this. They'll post a circuit, it looks like this, and you're thinking, what the F is going on here? And you just have no idea. You're like, and you've got to sort of work your way through the whole thing, which, I mean, that's useful. Go ahead and do that. But when you start out with the most sort of bare bones circuit, and then you begin adding the optimizations and the sort of protection aspects of it, then it's much easier to understand. So you can see you've got the basic circuit still here. You can see I've labeled these. If you look in the LM317 data sheet, it recommends a bypass capacitor on the adjust pin, which is what we've got right here. So I've added that. If you add a bypass resistor on the adjust pin, you have to have add a diode here, because let's say this thing's up at 400 volts, like it's doing, like it is, you know, like maybe we're using it, and then suddenly you turn the power off, or you short the device. Well, the voltage at a capacitor can't change instantaneously. That's what capacitors do. And so you'll end up with an LM317 with, 400 volts on the adjust pin. So your LM317 is dead. So what you do is you add a little diode here. Now normally this diode would be off, because this would be more positive than here by 1.25 volts. But if you turn the circuit off quickly and this is charged, it'll just allow a discharge path. There you go. Bob's your uncle. So that's what that's all about. They recommend 10 UF. You can see here, here's our voltage divider, but I've added an adjustment pot. So this is going to allow us to adjust the output voltage. Super useful on a regulator. So that's all that's going on there. You can see once again, we've got our 10 volt Zener that's running our gate, or a base on our pass device here. So it's a gate because it's a MOSFET. Instead of a resistor here, I've dropped a current source in there. So I'm just using a high voltage current source, like a depletion mode MOSFET or something, to run the Zener. That way, it doesn't matter what the voltage does over here. This is only ever going to get 5 milliamps. So that's perfect for that. You can see I've got a reverse voltage protection diode across the whole circuit up here. It's that little 1000 volt diode there. And so that way, if the voltages ever get out of whack, like let's say the input gets shorted, now suddenly instead of having more positive voltage over here than over here, let's say you turn it off, or something goes wrong over here, your cap goes bad and shorts or whatever, suddenly you've got 400 volts over here and 0 over here. Well, you've just destroyed all your devices, because none of these like to be reverse biased. They all like to have positive voltage on this side and negative voltage, less positive on this side. So if you put diode protection there. If that ever happens, if it gets above 0.6 of a volt or whatever, turns the diode on, and there you go. So that's what that's all about. Another thing that is recommended in the LM317 datasheet is to bypass the input pin close to the LM317 physically with a small value capacitor to ground. So it's tricky because in this circuit you wouldn't want to do that because this voltage here needs to respond instantaneously to voltage changes over here, because if this goes up or down quickly and this doesn't respond instantaneously, suddenly for a moment you've exceeded your 40 volt maximum across your device and your circuit is dead. And so that's why Michael Madia originally left this cap out of his design, but you can add it back in as long as you add a zener here. And I've used 10 just because I've got a bunch of 10 volt zeners, but anything between 10, which is it's going to be dropping less than that because of all this nonsense over here. So anything that's more than what it's dropping in operation, but less than that 40 volts that it can maximally take, you can put a zener here. That way, if something happens and this needs to respond quickly and this voltage exceeds the maximum of whatever this, it'll just go right around it with this zener right here. So it'll just pass right that way and save your device. So you can put that, and that further increases the ability of the LM317 to reduce ripple, just like this bypass cap. So the adjust pin bypass cap and the input pin bypass cap increase the ripple rejection of the LM317, which is what you want. You can see here I've got the current protection again from the last circuit. We've got a zener here. This protects the gate source junction voltage max. And if too much voltage is dropped across here, we'll turn this device off. And so you can set R4 to different values to get different amounts of current limiting at your output. And so this, you could actually short this circuit briefly. Of course, this is going to heat up like crazy. But you can short this circuit without destroying the components in it because of these current limiting devices there. So anyway, I hope that's been an interesting journey for you. When I first saw this circuit, I thought, what the hell is that? I have no idea how it works. It looked like magic to me, an LM317 in a 400 volt circuit. Didn't know how it worked. And so it took a while for me to sort of deconstruct, and I've deconstructed and reconstructed it here for you. And I really hope that you find this as fun and interesting as I did, and that you got something out of the video. So there you go. So these are all series high voltage regulators, and I might do another video perhaps on shunt high voltage regulators, because those are really cool too. And there's about 1 million different types of series high voltage regulators, and I haven't even scratched the surface here. So just know that. Anyway, hope you enjoyed the video.